Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Benjamin Franklin's Experiments and Observations on Electricity, published initially in serialized form starting in 1751 and as a collected volume in 1752, represents a watershed moment in the understanding of electrical phenomena. Its significance transcends a simple compendium of experiments. It is a masterful synthesis of existing knowledge, innovative experimentation, and groundbreaking theoretical advancements presented with remarkable clarity and persuasive rhetoric. The genesis of this work lies in the burgeoning scientific curiosity regarding electricity during the mid-18th century, fueled by earlier investigations of figures such as Stephen Gray, who demonstrated the conduction of electricity, and Pieter van Musschenbroek, inventor of the Leyden jar, the first capacitor. These predecessors established that electricity was a fluid capable of being transferred and stored. Franklin, however, moved beyond mere observation and sought to establish a comprehensive framework for understanding its underlying nature. Franklin's initial interest was sparked by correspondence with Peter Collinson, a Fellow of the Royal Society, who sent electrical apparatus to the Library Company of Philadelphia, which Franklin had founded. These devices provided the impetus for Franklin's own experimental pursuits, conducted in collaboration with colleagues such as Ebenezer Kinnersley, Thomas Hopkinson, and Philip Singh Jr. The collective's methodology was characterized by meticulous observation, carefully controlled experiments, and a relentless pursuit of coherent explanations. The core tenet of Franklin's electrical theory was the concept of a single electrical fluid rather than the then prevalent notion of two distinct fluids, vitreous and resinous. This single fluid, in Franklin's view, permeated all matter. An object in its natural state possessed a normal amount of this fluid. Rubbing different substances together caused an imbalance, transferring the electrical fluid from one object to another. An object receiving an excess of the fluid became positively charged, while an object losing the fluid became negatively charged. Franklin used the terms plus and minus, introducing a mathematical framework to describe electrical states, a conceptual leap of remarkable elegance and profound implications. Crucially, Franklin proposed the principle of conservation of electrical charge. The total amount of electrical fluid in a closed system remained constant. This insight, though not explicitly stated in modern mathematical formalism, is implicitly present in his descriptions. He explained charging by friction as a transfer of the electrical fluid rather than a creation ex nihilo. This established one of the earliest conservation laws in physics, predating similar formulations in mechanics and thermodynamics. The Leyden jar played a pivotal role in Franklin's research. He recognized it as a device for accumulating electrical charge, and he ingeniously connected several jars in series, creating what he termed an electrical battery, exponentially increasing the potential difference and discharge energy. His experiments with the Leyden jar allowed him to investigate the properties of electrical discharge, including its ability to cause shocks and arc across gaps. Perhaps the most celebrated, and certainly the most perilous, experiment described in Experiments and Observations on Electricity is the kite experiment. Franklin proposed to fly a kite during a thunderstorm, attaching a metal key to the kite string. If lightning was indeed electrical in nature, Franklin reasoned, charge would accumulate on the key, detectable by observing the sparks jumping between the key and his hand. This experiment, though fraught with danger, provided compelling evidence for the identity of lightning and electricity. It demonstrated that lightning possessed the same properties as electricity, produced by frictional machines, confirming Franklin's hypothesis. It is worth noting that while Franklin often receives singular credit, the experiment was likely performed collaboratively, and other individuals independently conceived of similar experiments, some with tragic consequences. The immediate impact of Experiments and Observations on Electricity was considerable. Franklin's clear writing style and compelling experimental demonstrations captivated both the scientific community and the general public. His work was translated into numerous languages, disseminating his ideas across Europe and beyond. He was elected a Fellow of the Royal Society in 1753 and awarded the Copy Medal, its highest honour, for his contributions to electrical science. Franklin's theories were rapidly adopted and expanded upon by other researchers. His single-fluid theory largely supplanted the two-fluid models, becoming the dominant paradigm for understanding electricity. His terminology of positive and negative charge remains standard usage today. The concept of electrical conservation permeated later discussions of electrical phenomena, forming the basis for more sophisticated theoretical frameworks. One significant application of Franklin's work was in the development of lightning rods. Based on his findings that pointed objects efficiently discharge electricity, he advocated for installing grounded metal rods on buildings to protect them from lightning strikes. This invention, a direct consequence of his scientific investigations, saved countless lives and prevented extensive property damage. It demonstrates the pragmatic application of theoretical knowledge, a hallmark of Franklin's approach to science. Later use and evolution of Franklin's work saw the development of more sophisticated mathematical models of electricity. While Franklin employed qualitative descriptions, later scientists such as Henry Cavendish and Charles Augustin de Coulomb quantified electrical forces and potentials. Coulomb's law, which describes the force between stationary charges, builds directly upon Franklin's conceptual framework, providing a mathematical expression for the attraction and repulsion of charged objects. The development of electromagnetism in the 19th century, spearheaded by figures such as Hans Christian Ørsted, Michael Faraday, and James Clerk Maxwell, further refined and extended Franklin's ideas. Maxwell's equations, which describe the behavior of electric and magnetic fields, represent a complete and rigorous mathematical theory of electromagnetism. While Maxwell's theory transcends Franklin's initial formulation, it remains firmly rooted in the fundamental principles Franklin established, including the conservation of charge and the nature of electrical forces. It is also worth mentioning the effect Franklin's work had on the burgeoning field of medicine. His experiments with electrical therapies, while often crude by modern standards, paved the way for future research into the physiological effects of electricity and its potential applications in treating various ailments. Critiques of Franklin's work were relatively few, but they did exist. Some scientists questioned the validity of his single fluid theory, arguing that it failed to adequately explain certain phenomena. Others criticized the anecdotal nature of some of his experiments, suggesting that the results were not always reproducible. However, these criticisms were largely overshadowed by the overwhelming success of Franklin's work in explaining a wide range of electrical phenomena. Furthermore, Franklin's experimental approach, while not always rigorously controlled by modern standards, was remarkably innovative for its time. His willingness to challenge prevailing theories and his emphasis on empirical evidence represent a significant contribution to the scientific method. The reception of experiments and observations on electricity was overwhelmingly positive, both within the scientific community and among the general public. Franklin's fame as a scientist contributed significantly to his later political career, lending him an air of authority and intellectual gravitas. His scientific achievements enhanced his reputation as a polymath and contributed to his image as an enlightened statesman. The direct influences on Franklin's work are readily identifiable. He was deeply influenced by the writings of earlier electrical researchers, including Stephen Gray, Piet van Musschenbroek, and William Watson. He also drew upon the broader intellectual tradition of the Enlightenment, embracing empiricism, rationalism, and a commitment to scientific progress. Newton's Principia Mathematica, while not directly addressing electricity, provided a model for a comprehensive and mathematically elegant explanation of natural phenomena, which Franklin sought to emulate in his own. The direct influence of Franklin's work on others is equally evident. Figures such as Ebenezer Kinnersley, who collaborated with Franklin in his experiments, became prominent electrical researchers in their own right. Joseph Priestley, the discoverer of oxygen, drew heavily on Franklin's work in his own investigations of electricity. As Sandro Volta, inventor of the voltaic pile, acknowledged Franklin as a major influence on his Franklin's experiments and observations on electricity therefore occupies a pivotal position in the history of science. It represents a masterful synthesis of existing knowledge, innovative experimentation, and groundbreaking theoretical advancements. His work not only transformed our understanding of electricity, but also had profound implications for the development of science and technology more broadly. It embodies the spirit of the Enlightenment, demonstrating the power of human reason and empirical observation to unlock the secrets of the natural world. The legacy of Franklin's work continues to resonate today, serving as an inspiration for scientists and engineers seeking to address the challenges of the 21st century. He demonstrated that scientific inquiry could be both intellectually stimulating and practically useful, contributing to the betterment of society. One could even argue that the clarity and accessibility of Franklin's writing style served as a model for science communication, influencing generations of scientists and popular science writers. He recognized the importance of conveying complex scientific ideas in a manner that could be understood by a broad audience, contributing to the democratization of scientific knowledge. This emphasis on clarity and accessibility remains a crucial aspect of effective science communication today. Furthermore, Franklin's work on electricity had a profound impact on the development of electrical engineering. His experiments with Leyden jars and electrical batteries laid the foundation for the development of capacitors and other energy storage devices. His investigations of electrical discharge led to the development of spark ignition systems, which played a crucial role in the development of internal combustion engines. It is also important to consider the social and political context in which Franklin's work was produced. He was a prominent figure in the American colonies, actively involved in public life and the movement for independence. His scientific achievements enhanced his reputation and credibility, contributing to his influence in colonial affairs. His scientific pursuits were intertwined with his political aspirations, demonstrating the interconnectedness of science, technology, and society. In conclusion, Experiments and Observations on Electricity is a work of enduring significance in the history of science. It represents a watershed moment in the understanding of electrical phenomena, contributing to the development of electrical engineering and influencing broader trends in science communication and public engagement with science. Franklin's legacy extends far beyond his scientific achievements. He remains an icon of the Enlightenment, embodying the values of reason, empiricism, and a commitment to the betterment of society. His work serves as a reminder of the transformative power of scientific inquiry and its potential to shape the world in profound ways. His contributions established fundamental principles which remain crucial cornerstones of modern physics. Moreover, the accessible style with which he presented his findings influenced generations of scientific communicators. The echoes of Franklin's kite soaring amidst a thunderstorm continue to resonate throughout science to this day.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.